Hello everyone. Today I'll be discussing about the second technique, that is binary BPSK, also known as binary phase shift gain, and we are discussing the coherent modulation techniques, so also known as coherent binary PSK. As the definition goes, PSK is the counterpart of phase modulation what was done in the analog domain, and in a binary PSK system there is a phase shift of 180 degree observed between symbol 1 and symbol 0. Let me look at the waveform first and then I'll come back to equations. So my carrier is analog and the baseband digital data is represented here by a sequence of bits, ones and zeros. So during binary 1, when the input is high, whatever is the carrier, exactly same carrier is reproduced at the output in phase with the, output is in phase with the carrier. But when there is a binary 0, you can see that the waveform undergoes a 180 degree phase shift. So whenever there is a transition from 1 to 0 or 0 to 1 in the input waveform, we can see a 180 degree phase shift in the output waveform. So the waveform is 180 degree out of phase compared to that of the carrier waveform. That is the basic definition of phase shift gain. That is, the phase of the carrier undergoes a change, in accordance with the baseband input signal, keeping the carrier amplitude constant. The amplitude of the carrier is not changing. The amplitude is still constant here. You can see there is no change in the amplitude, only there is a change in the phase. And when I say binary phase shift gain, so binary means there are two symbols, 1 and 0, and the phase shift is 180 degree. We have other variety of derived techniques of PSK such as QPSK, pi by 4 QPSK, pi by 4 PSK, MRE PSK, and so on. There are many. We will be discussing subsequently that also. So the simplest case, when I say BPSK or binary PSK, is also known as only PSK, is also referred as only phase shift gain, and there is a phase shift of 180 degree. So we can represent the modulated signal as a pair of signals. So modulated signal S of t can take a form of S1t or it can take a form of S2 of t. Let's say S1 of t represents symbol 1 transmission and S2 of t represents symbol 0 transmission. So the way we have represented our ASK signal as A cos 2 pi fct, the carrier. Similarly, the amplitude is represented as root over of 2 ps there, and ps is signal power, which is the ratio of bit energy or signal energy divided by bit duration. So EB is bit energy and TB is the bit duration. So energy contained in 1 bit, and this is the energy. This is the time for taken for 1 bit transmission. So S1 of t is the equation of binary 1. Similarly, binary 0 is represented by S2 of t, and we see what is the difference when there is a change from 1 to 0. There is a phase shift of 180 degree. So in the waveform for binary 0 S2 of t, we have written cos of 2 pi fct plus pi. Pi is this additional phase which comes into picture because of the definition of BPSK. Now cos of theta plus pi is equal to minus cos theta. So we can say this is also equal to minus of root over of 2 EB by TB cos 2 pi fct. So very simple, BPSK represent binary 1 is represented as root over of 2 EB by TB cos 2 pi fct, and binary 0 is represented as S2 of t equal to minus root over of 2 EB by TB cos 2 pi fct. This is the waveform we have seen. Now we can rearrange the modulated signal and write it in terms of signal coefficient and carrier function, the way we were doing it for ASK. Now if you look at S1t and S2t, the two symbols represented in the BPSK waveform, both have a carrier cos 2 pi fct. So there is only one carrier, hence BPSK is also one dimensional modulation technique. We can rearrange this equation and rewrite that as root over of 2 by TB multiplied by root over of EB into cos 2 pi fct. If I rearrange in that part, in that way, I can say that Root over of 2 by tb cos 2 pi fct is totally the carrier function phi 1 of t. Look at this expression. Similar way we did for ASK also. Just look at equation number 13. Just break this down. So it can be written as root 2 by tb multiplied by root over of eb. So root over of eb, write it this side, and the remaining term is root over of 2 by tb cos 2 pi fct. That part is your carrier, and the signal coefficient is root over of eb. So that is written over here. So carrier is represented as root over of 2 by tb cos 2 pi fct. So I can say s1 of t is equal to, the signal coefficient is root over eb multiplied by phi 1 of t, and s2 of t is minus root over of eb with phi 1 of t. There is just a difference of this minus symbol which indicates a 180-degree phase shift. Okay. Now, so the BPSK is a single dimension modulation technique, one carrier function. If I want to find out what is the projection of signal waveform S1 of t on phi 1, I can compute it as signal coefficient S11, which is integration of S1t multiplied by phi 1 t dt. But S1 does not. Okay, so if I want to find out what is the projection of signal 2 on phi 1, then the formula I can write it as integration S2 of t phi 1 of t dt, which is equal to minus root over of eb. So this signal coefficients we can also represent as, when I say S1 of t is equal to root over of eb into phi 1 t, this root eb can be written as S11. So I can say S1 of t is equal to S11 into phi 1 of t. That S11 is the signal coefficient, or I can say projection of signal S1 on carrier phi 1, that is S11. Similarly, I can say this as this minus of root over of eb as S21, that is the projection of signal 2 on carrier 1. So that is, this signal coefficient is represented as S21. Same thing is written over here. Okay. Now coming to signal space diagram. So one dimensional modulation technique, again easy, simple, one line, phi 1 of t, one dimensional, and two message points, 0, message point 0 and message point 1. Symbol 0 magnitude minus root over of eb, and symbol 1 magnitude is plus root over of eb. If I want to do a decision boundary, I will draw the boundary exactly running in the midway of the 2 points. So this is minus root over eb, this is plus root over of eb. So definitely the decision boundary will run through 0. Okay, so the region towards the left of the decision boundary, I am calling it as Z1, and the region to the right hand side of the boundary is region Z2. This is the signal constellation diagram. Coming to generation of BPSK, very simple. We have a product modulator. We have a input waveform in polar form. You know what is a polar form? When binary 1 is represented by positive magnitude and 0 is represented by negative polarity amplitude, then it's called a polar format. That gets multiplied with the phi 1 of t, and what available is a BPSK signal. Looking at the coherent detection of BPSK, first the received signal is multiplied with carrier integrated inside a correlator and then decision divide, which is exactly same as the detector discussed for ASK. So absolutely no change. Here only thing is the threshold, we have made it as 0. So if x1 is greater than 0, choose binary 1. If x1 is less than threshold 0, then choose binary 0, or take a decision in favor of symbol 0. Is exactly same. Detector is exact. BPSK is exactly same as that of ASK. Now coming to the calculation of error probability in BPSK. The process remains the same. The only thing is now the symbol points will vary, their magnitude will vary, and hence the probability for error expression will also vary. Okay. Now let the received signal in addition with noise. So S of t is the modulated BPSK signal, gets added up with AWGN of 0 mean and variance N0 by 2 when transmitted in channel. So whatever is received is X of t, and the received signal X of t is equal to S1 of t, which is S1 of t plus W of t. So S1 of t already we know it's equal to root of EB into phi 1 of t, or X of t can be equal to S2 of t plus W of t for 0 transmission. Let us assume that symbol 0 was transmitted, then what will be the output of correlator? Same process is same. The output of quantity x1 is multiplication of x of t into phi 1 and then integrate over one bit duration 0 to tb. So x1 will be equal to integration 0 to tb x of t into phi 1 of t. So that is written over here. So x1 output of correlator is equal to integration 0 to tb x of t into phi 1 of t. So we assume that symbol 0 is transmitted. So what is the signal waveform corresponding to 0? For 0 we have taken x of t is equal to s2 of t plus w of t. So in place of x of t I will write here s2 of t plus w of t into phi 1. Now integration is broken into two parts. The first integration is integration 0 to tb s2 of t into phi 1 t dt plus integration w of t into phi 1 of t dt. Both integration limits is from 0 to t. Okay. So what is this? Projection of signal to S2 on phi 1, or this is the coefficient S21 we have seen earlier. The coefficient S21. Yes. So what was the coefficient x21? I told you S21 means it is the projection of signal 2 on the carrier phi 1 of t, and the value is minus root over of EB. So we have substituted there. So we have substituted in place of this is S21, substituted minus of root over EB plus noise component in the direction of carrier signal is W1. W multiplied by phi 1t integrated, we get a component, noise component, which is W1. So x1 is equal to minus root over EB plus W1. Let us now find out the mean of this value x1 and the variance of x1. So what will the mean of x1? Mean of x1 is E of x1, and expected value of x1 equal to expected value of x1 is minus of root over EB plus W1, which is equal to expected value of minus root over EB plus expected value of W1. Expected value of noise, we have already assumed that AWGN noise is of 0 mean. So this value is 0. So what we are left with is the expected value of x1. So we have only one value. So the mean value is the same because there is only one value. So mean is also same as the value. So that's equal to, so mean of E of x1 is equal to minus root over of EB. Now variance of x1 is equal to variance of minus root over EB plus W1. So that's equal to variance of minus of root over EB plus variance of W1. Now what is the variance of minus root over of EB? How do we find out variance? Variance is equal to the value, the signal value, my variance of this quantity is equal to this quantity minus its mean, right, whole square. So what is the quantity? Minus root over of EB. What is this mean? Minus root over. So the quantity minus root over of EB minus of its mean, and mean value is minus. So minus of minus is plus. So minus root over of EB plus root over of EB whole square. So that's equal to 0. So variance of this quantity is equal to 0 plus variance of the white noise is N0 by 2. So finally the variance of x1 is N0 by 2. Okay, so using these two values, that is the mean of x1 as minus root over of EB and the variance of x1 as N0 by 2, we will make substitution of the two values in the conditional PDF expression. So being the noise being a Gaussian distribution, I will write down the conditional probability f x1 of x1, condition that I have assumed that 0 is being transmitted, is equal to, this is the PDF, the probability density function equation of a Gaussian distribution. Students, you have to remember this. These are the basic equations used n number of times in any communication theory or subject. Okay, so especially the equation of Gaussian distribution, Rayleigh distribution, will be using a number of times. So this is a well-known equation for determining the probability density function of a Gaussian distribution. So that is written, and we are going to substitute now the variance sigma square, and the mu is the mean. So whatever we have obtained in the previous steps. Okay, so the mean is minus root of EB and the variance is N0 by 2. I'll be substituting in place of mu and sigma square, and this is what I get. So sigma is N0 by 2, sigma square is N0 by 2, 2 gets cancelled. So in place of mu minus EB, and already minus is there, so minus of minus is plus root over of EB whole square divided by 2, again sigma square N0 by 2. So the resulting equation is 1 divided by pi root n naught multiplied by e to the power minus of x1 plus root over of eb divided by root over of n naught square. So what is the probability of error? So I look at the signal space diagram. That's the conditional probability expression we wrote now. Now what is when the error will happen? If I am transmitting 0, the received signal should lie in which region? In region Z2, right? But if the received signal due to the interference of noise, the received signal point lies in region Z1, the decision will be taken in favor of message point 1, which is a wrong decision. Okay, so and the region Z1, you can see here, it extends from 0 to what? 0 to infinity, right? So while determining the probability of error expression, we can say that x1 lies from, so there will be an error if the received signal lies in region Z1, that is in the region extending from 0 to infinity. So x1 lying from 0 to infinity. So the probability of error for zero transmission is equal to, probability can be found out by integrating the PDF, as we have already seen in ASK also. Similar thing I have explained. So this is the PDF. So I will integrate that. And what is the integration limit? 0 to infinity. Error will occur only when the received signal point x1 lies from 0 to infinity. So 0 to infinity, you are integrating the conditional PDF expression. So whatever we obtained in the previous step. Okay. Equation number 20. Just going to rewrite equation number 20 or substitute equation number 20 over here. Okay, so the magnitude part is taken out of integration, and inside the integration I am left with exponential term e to the power minus of this quantity square dx1. Let me again assume that, let's say the quantity inside this is totally is equal to z. So this is z, and then I can find out what is the change in z, dz, and this side I can get dx1 divided by n naught plus 0, or I can get dx1 as root over of n naught into dz. Similarly, I can change the limits of integration. When x1 equal to 0, the value of z is root over of eb by n naught, and when x1 is infinity, z is also equal to infinity. Now changing the variable of the integration and changing the limits, we have this particular expression, and with few cancellation here of root over of n naught, root over n naught. So the left out equation is 1 by root over of pi integration eb by n naught to infinity e to the power minus z square dz. Again, I can use the complementary error function definition to rewrite the above expression. Multiplying and dividing numerator denominator by 2, I can rearrange this equation, and I can say 1 by 2 separately. So root 2 by root pi into this entire thing I can replace by the definition of the complementary error function. What is the lower limit? That is u is equal to root over eb by n naught. So I can say 1 by 2 ERFC of u. So u is the lower limit of the integration, that is root over of eb by n naught. The way we obtain probability of error for zero transmission, similarly probability of error with a simple one transmission will be exactly the same, and the probability of sending or transmitting 0 and 1 is same, that is 1 by 2. So the average probability of error expression is p of 0. Yeah, so the average probability of error expression is PE equal to P of 0, probability of sending 0 multiplied by probability of making error while sending 0, plus probability of sending 1 plus probability of error for making an error while sending 1. Just substitute, this is 1 by 2, this is 1 by 2, P of E of 0 is equal to PE of 1, that is 1 by 2 ER of FC of root over EB by naught we derived. So the final expression of the average probability of simple error in a phase shift keying technique is 1 by 2 ER FC of root over of EB by n naught. Thank you.